Okay, it says it's recording, so I'll get started. Sorry it's taken so long. I've ran into every kind of problem that could possibly be imaginable. I ran into. Anyway, so here we go. I am going to finish section 4.3 that we started on Friday, and all I did was I was able to give you some theorems and some definitions and stuff. Need to give you a few more, and then we'll do some examples. All right. I hope you all are doing well. Don't be stressed about this, and it'll all work out. Promise. Yes. Okay. All right. Let me push a few buttons to switch this thing. Do. Add, share. All right. Hopefully that is working. Okay. Here we go. Let me hide this. Okay. All right. So what we did on Friday was we did I gave you the definition about given n by n matrices A and B, we say A is similar to B if and only if there exists a non-singular n by n matrix K such that B is equal to K inverse times A times K. And then, so that's if they're similar. Another definition saying that given n by n matrix A, so there's square matrices, right? We say that A is diagonalizable if and only if A is similar to a diagonal matrix D. Remember, a diagonal matrix is when you've got zeros everywhere except down the diagonal. And they don't all have to be the same number down that diagonal. All right, then we had the theorem. Again, I gave this to you on Friday. The n by n matrix A is diagonalizable if and only if it possesses n linearly independent eigenvectors, which are all those k ones, with corresponding eigenvalues, all the lambdas, where capital K, so that's that K we were talking about, is this matrix made up of the eigenvectors, and K inverse times A times K ends up turning out to be the diagonal matrix made up of all the eigenvectors. And then when A is diagonalizable, we say that A possesses a complete set of eigenvectors. I'm pretty sure I gave you this one on Friday also, that if we let all these lambdas be the distinct, that means different, eigenvalues of the n by n matrix A, and let all of these k's be the corresponding eigenvectors, then each of those eigenvectors are linearly independent. I think that's where we stopped on Friday. We also have a corollary that says that if n by n matrix A has n distinct eigenvalues, then it possesses a complete set of eigenvectors, and A is diagonalizable. So if it's an n by n matrix and has n different eigenvalues, then it possesses a complete set of eigenvectors, and A is diagonalizable. And then in general, remember this is your characteristic polynomial. You'll have lambda minus all of these eigenvalues, and then the m ones are like exponents, right? And so you'll have all these factors. You can multiply them with all these factors, where if you add up each of the exponents, then it'll equal n, the size of your matrix, right? Where mi is the multiplicity of each eigenvalue. So if n is the number of independent eigenvectors of the eigenvalue, then your n is going to be bigger than 1, but smaller than m, and A is diagonalizable if and only if n is equal to m. All right, so let's do an example. We're going to find all kinds of things for each of these. For each matrix, we're going to find the eigenvalue of A and their multiplicity and the corresponding eigenvectors, and determine if A is diagonalizable. If it is, then we're going to find K and diagonal matrix D such that D is equal to blah, blah, blah. Okay, so let's start with example 1. We're going to find all of that stuff. Yeah. Try to make my hand not cover it. Okay, so if A is -1, -2, -2, 2, remember you'll do lambda times the identity matrix minus A, and that'll give you a lambda minus -1, a +2, a +2, and then a lambda minus 2. All right, so finding the eigenvalues and their multiplicity. What you want the determinant of the lambda I minus A to equal 0, right? And if you remember, that's that characteristic polynomial is equal to that, right? So the determinant here, you multiply down the diagonal. So lambda plus 1 times lambda minus 2 minus 2 times 2, which is 4, not 2. See, I don't have you guys to catch my typos this time. All right, so we multiply those out. That would be what? Lambda squared minus 2 plus 1, so a -1 lambda minus 2 and then minus 4, so a -6. And we want when is this equal to 0? So let's factor it. Two numbers that multiply to -6 but add to -1 would be lambda minus 3 and lambda plus 2. And we want when those are equal to 0. And so, slide that up. Setting each of those factors equal to 0 will give you a lambda is equal to 3, which has a multiplicity of 1, since there's not an exponent on this factor, right? There's an invisible one there. Or lambda equals -2, which also has a multiplicity of 1. Right, so those are they asked us for eigenvalues first and their multiplicities. So there's your eigenvalues with their multiplicities. Then we find their corresponding eigenvectors. Yeah, so when lambda is 3, we're going to be plugging 3 into the lambda in this guy. So 3 plus 1 will give you 4, and then it's a 2. That's a 2. 3 minus 2 will give you a 1. And we're solving when are those equal to 0. I would do row 1 plus -2 row 2 and get a 0. And then 2 plus -2 will also give you 0, and then you got a 0. So you could divide by 4. I would just go, okay, that top row says 4x1 plus 2x2 is equal to 0, which means x2 will equal -2 times x1. And so if you let x1 equal a, then x2 would equal -2 times a, which gives you an eigenvector of a comma -2a. And then we just usually factor out that a. So it would be a 1 comma -2. So there's the corresponding eigenvectors, right? Because remember, there's an infinite amount of them since that a is any real number. It corresponds to the eigenvalue of 3. We'll do the same thing with lambda when it's -2. Plugging that in, you'll get a -1, a 2, and a -4. And then for this one, I would do a 2 times row 1 plus row 2, which would be a -2 plus 2 is 0. 4 plus -4 is also 0. Well, isn't that nice? -1, 2, 0. All right, so that top row says I've got -x1 plus 2x2 equals 0, which means that x1 will equal 2x2. So I'll let, this time I'll let x2 equal a. So then x1 will equal 2 times a. And that'll give me 2a comma a, which means it's a times 2 comma 1. Here we go. All right. We definitely have 2 linearly independent eigenvectors, and so yes, it is diagonalizable. since there are two linearly independent eigenvectors. All right, then they want us to find, what's next? They want us to say, if it is diagonalizable, let's find K and diagonal matrix D, so that D is equal to K inverse times times A times K. All right, so part C. What you'll do is you'll use the columns are your eigenvectors for K. That's what you'll use. The columns of K are your eigenvectors. And so you'll say K is, the first one was 1, -2, and the second one was 2, 1. There's K. Now, and then D, to find, is it still, yeah. D is K inverse times A times K. Yeah. And so this would be, need K inverse. I need A was -1, -2, -2, +2. K we just found was 1, 2, -2, 1. And then to find the inverse of K, if you remember, you switch the main diagonal, you switch these, they're both 1, so it'll look the same even though I switched them. And then these two guys stay the same but opposite in sign. So this +2 becomes a -2, and this -2 becomes a +2. So that's how you find the inverse of a 2 by 2. Now, right, so then what do we do next? Let's multiply them. So I'm going to multiply the first two first. It's a 2 by 2 times, all of them are 2 by 2, so you'll have 2 by 2. So you get a, -1 plus a +4, which will give you a +3. We've got a -2 plus a -4, which gives you a -6. -2 plus a -2 will give you -4. And then -4 plus a +2 gives you a -2. And then I still have, that was these two together. And I still have 1, 2, -2, and 1. And then we'll multiply those two together also, which will give you what? 3 plus -12, no, plus +12. So that gives you +15. 6 plus a -6 gives you a 0. -4 plus +4 is 0. And then -4 plus -2 will give you a -2. No? No, did it wrong. -8 plus -2 is a -10. That's what I didn't grab, was my whiteout. And you guys know I need my whiteout, huh? All right, there we go. That's better. Okay, so that means that you could, there is a 3 in, no, what's in common? A 5 in common, yeah? And so you can factor that out and make it that they diagonalize your D, your diagonal matrix, right, would be 3, 0, 0, -2. And that's the same thing as writing. You can write the diagonal matrix composed of, these are the diagonal numbers. That also works also, just so you recognize that notation. I think maybe the book does that sometimes. Okay, there's example 1. Let's do another one. And sure, hopefully no errors. I don't think I see any. So that's good. Okay, Let's do example 2. Same directions, but now A is 1, -8, 2, -7. Yeah? And our lambda times the identity matrix minus A would give me lambda minus 1, 0 minus -8, so that's a positive 8. This would be a -2, and that would be a lambda plus 7. Now, and hopefully you guys remember that. I just remember that somebody asked me that last time. I already did it on the last example, but in case you were confused, remember lambda I would be lambda 0, 0, lambda. Yeah, and so then minus this matrix A. So hopefully you remember that anyway, since I already did it. But okay, so we got that, and then to find your eigenvalues, you do find the characteristic polynomial, which is, remember, the determinant of that matrix I just found right there. And that's going to be multiplying down the diagonal, lambda minus 1 times lambda plus 7, and then minus a -16, so plus 16. Yeah. And then that would give you, and we want when that's 0. Right? So that'll give you what, lambda squared plus 7 minus 1, so a plus 6 lambda, minus 7 plus 16 gives you a plus 9. That ends up factoring as lambda plus 3 quantity squared. And so you get your eigenvalues when this characteristic polynomial is 0, which means that your eigenvalue is -3, and this one has a multiplicity of 2. So um, one eigenvalue this time with multiplicity of 2, which is a 2 by 2, so should match up. Okay, so let's find the eigenvector corresponding to it. So when lambda is -3, it would give me -3 minus 1 gives you -4. We have a positive 8. I got a -2 and then a positive 4. We want to solve for when these are 0. And so I would do row 1 plus -2 times row 2, which would be -4 plus positive 4, 8 plus -8, and then 0. Yeah. And then that tells me that -4x1 plus 8x2 is equal to 0, which then gives me that x subtracted. So x1 is equal to 2 times x2. And if I let x2 equal a, then x1 will equal 2 times a, which then gives me an eigenvector of 2a comma a, factoring out the a, 2 comma 1. All right, so there's my eigenvectors corresponding. Part B says, is it diagonalizable? So notice that A has only one linearly independent eigenvector. So here it's when they were talking about those n's and m's, this is n is 1, right? But m was 2, right? It's your multiplicity, right? You had a multiplicity of 2. And since m is not equal to n, so the number of linearly independent eigenvectors does not match the multiplicity, right? And so since they're not equal, then it is not diagonalizable. And so we can't even do part C because this one's not diagonalizable. Hopefully the next example we have, okay, so the multiplicities of all of your eigenvalues need to add up to how many, need to match how many linearly independent eigenvectors you have. We only had one eigenvalue with a multiplicity of 2, but then we turned out to only have a single linearly independent eigenvector, so not diagonalizable. All right, that was example 2. Let's do another one, example 3. And this one will take a little bit longer because there's more. We're going to do a 3 by 3. All right, so this time A is 1, 0, 0, 0, 3, 7, 1, 1, negative 3. And so your lambda times the identity matrix minus A would be lambda minus 1, 0 minus 0, and a 0 minus 0, 0 minus 0. This one is lambda minus 3. This would be in 0 minus 7, 0 minus 1, 0 minus 1, and then lambda minus negative 3. All right, so there's your thing. I don't see a typo, yay. All right, so A wants to know, let's find the eigenvalues. We start by finding the characteristic polynomial. Now eigenvalues come from setting this guy equal to 0. So we have a 3 by 3 this time, but ooh, nice, 0 and 0. That's going to be so friendly, right? Because remember, you're going to take, you would normally take, oof, what did I do? I hit something. Okay, hopefully that didn't mess that up. You're going to have to bear with me, guys. It's just a little bit of a learning curve, just a little bit. Okay. All right, so I'm taking this guy, and remember, ignoring, and then times the determinant of this one. But then remember, it would have been minus 0 times the other determinant, and then plus 0 times that determinant. Lovely. This is going to be so much easier. Famous last words, right? Okay, so we got lambda minus 1, and then times, I would multiply down, so I'm ignoring top row, and I'm ignoring that guy. So we'll have a lambda minus 3 times lambda plus 3, and then minus negative 7 times negative 1, so a positive 7. Now, that's the difference of 2 squares. So that ends up being a lambda squared minus 9, and then a minus 7. So that's nice, right? Do you remember that this guy would be lambda squared minus 9, and then minus 7. So a lambda squared minus 16. Yeah. And then that's the difference of 2 squares, so that factors. Yeah, so we'll go lambda minus 1 times lambda plus 4 times lambda minus 4. And we want when this is equal to 0. And so our eigenvalues are lambda equals 1, and that has a multiplicity of 1. And lambda equals negative 4, which also has a multiplicity of 1. And lambda equals positive 4, which also has a multiplicity of 1. You get your multiplicities by the exponents on the factors. So 1, 1, 1. That's how I'm knowing that they all have a multiplicity of 1. All right, so there's your eigenvalues, all having multiplicity of 1. So that means we need to find 3 linearly independent eigenvectors in order for this to be diagonalizable. All right, so what are we doing next? We have those. We need the eigenvectors. Okay, so when lambda equals 1, you would have a 0, 0, 0, 0, negative 2, negative 7, negative 1, and 4. Yeah. And so what I'll do first is let's do a swaparoo. I'm going to swap rows 1 and 3. Row 3. That's row 3. I'm going to swap them. And I'm also, and hopefully it's okay with you that I do this at the same time, I'm also going to make this guy a positive one when I do it. So I'm also going to go, well, I'll do that in a minute, I guess. Okay, so we're going to swap them. -1, +4, 0. And then row 3 will be the 0 row. Perfect. 0, -2, -7, 0. Okay, and then I'm also going to do now a negative row 1 so that I'm going to change, get a different color. I'll change this guy to a positive, that guy to a positive, and that one to a negative. So I changed all the signs, yeah. All right, then I want to get rid of this one right there using the -2. So I'll do row 2 plus negative, nope, I don't need to do negative, plus a positive 2, because that's already a negative and that's positive. Okay, so +2 times row 1. All right, so we got 0 plus 2 times 1, so that changes that to a 2. -2 plus 2 will give you a 0. -7 plus -8 gives me -15, and then that's a 0. And then I can change, I can get this, I mean, I could leave it and do it after, but I'll just do it right now. -1/2 times row 2. So I get a 0, a 1, a positive, 7 halves, and then a 0. And then this third row is still all zeros. Okay, so what does that give me? That gives me, first row says 2x1 minus 15x3 is equal to 0. And row 2 says x2 plus 7 halves x3 is equal to 0. So that you end up with a x1 is equal to 15 halves times x3, and x2 would be a -7 halves x3. So we're going to let x3, and if we had let it equal 2 times a, then I don't have to deal with fractions, which is nice and friendly. Yeah, so if x3 is equal to 2a, then x1 will equal 15 times a, and x2 will equal -7 times a. So that my eigenvector, I'm going to go ahead and just factor out the a right now, okay, would be x1 first, so 15, then x2, and then x3. All right. I wish I had a timer on what time I started this. I'm going to do this because nobody wants to just see me. I mean, it's what you guys are doing is see me work it out. But for the next two, I think you get the point, right? You can work this out yourself. I'm just going to say when you do the same process. Do the same process for the other two eigenvalues, right? And pause my video right now, yeah, so that figure out what's your eigenvector for when lambda equals -4. Pause the video, do it on your own, and you should end up with 0, 1, -1 times a. Yeah. And then, if you didn't pause it before, definitely pause it now. Well, right now. Do the same process. Plug 4 into lambda and do the same process of finding your eigenvector. Did you pause? If you don't practice it on your own, you're not going to learn how to do it when you get to the test. So pause the video and then come back and confirm that you got the same thing. Yeah? All right, so welcome back. I wonder how many of you actually did it. That'll be funny. Okay. For when it's 4, your eigenvector is 0, 7, 1. Okay. Keep in mind, you may have done things a little bit differently. So if you should definitely get a 0 here, no question. But if you got a -1 and then a +1, not a problem. Because remember, A can be any real number. So any multiple that you have in here is also true. And then same thing here. You should definitely get a 0 here. But if you had like let's say you subtracted differently from me, you could have had a -7 here and a +1 there. I mean, no, sorry, negative and a negative, right? It should um, match that way. All right. So we have 3 linearly independent eigenvectors. And so this is yes, it is diagonalizable. And that's since the multiplicities were 3, they added up to 3, right? And we have 3 linearly independent eigenvectors. So yes, it's diagonalizable. And so then they want you to find K. Well, K is just going to be the matrix where you make these eigenvectors now your columns. So I'll make my first column 15, -7, 2, and then a 0, 1, -1, and then a 0, 7, 1. So there's K. Now, to find K inverse, right, because we got to find D also, right, we got to find that diagonalizable. Well, okay. Should I show it to you? Now listen, remember I told you, your D is going to be the diagonal matrix of your eigenvalues. So, um, spoiler alert, I shouldn't have told you that yet. Okay, pretend I didn't tell you that. Let's keep on going. Let's find K inverse, and then it'll bring it all together. Yeah. All right, so to find K inverse, it's a 3 by 3. You have multiple ways that you have learned already. My go-to is I'm going to put K and then I'll add the identity matrix after 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah, you augment it with that. And then you do row operations and it looks like I did math magic again. Okay, so you do row operations so you could pause the video, right? Do some row operations and you want to end up getting where um, your final answer after all your row operations is a 1, 0, 0, a 0, 1, 0, and a 0, 0, 1 on this side. And then over here is your inverse, right? So pause it, work it out. Pause. Okay, welcome back. I hope you paused it and you worked it out. And I hope you got a whole bunch of ugly fractions because that's what you should have gotten. I got a 1 over 15, 0, 0. I got a 7 over 40, 1 over 8, -7 over 8. Yeah, ugly, right? That guy and that guy. And then if you remember, this is the identity matrix now. And so this is the inverse of K. And if you were to go through and go um, K inverse, this guy, oof, times A times K, right? You would have that whole guy and then, okay, why am I doing this? Why? Why? Right? K inverse would go here and your A was, I don't even have it in front of me anymore. Oh, yeah, I do. 0, 3, 7, and 1, 1, -3. And then K was where your eigenvectors were, your columns, 0, 7, 1. And if you multiply these out, you'd have to do like multiply these two together and you'll get a 3 by 3. And then you multiply it times that guy, which is a 3 by 3. And you will end up with a 1, 0, 0, and a 0, negative 4, 0, and a 0, 0, 4. Right? Do you see it is a diagonal matrix where along your diagonal are all of your eigenvalues. Yeah. So that's your D. Now, am I going to have you do this the long way? I think I do have you confirm it. Like, I'm okay with you doing this, but I think I say and confirm that your K was correct and all that. So, and then also your book may write this as diag parentheses, and then you write the 1, negative 4, 4. That's what that notation means. It's the diagonal matrix. Okay, there we go. That is section 3. And let's see, stop presenting. You're seeing all my things. I am still working out the quirks. We will see. Stop presenting. Didn't I say? Okay, there we go. I'm back. Hi. All right. Hopefully that made sense. I will have office hours coming soon. They want me to start doing them on Monday. Text me though. Text me or send me an email if you're having trouble. Hopefully you're staying up on this. Don't let it go, because when we come back, testing. Yeah. As of right now, that's what's going to happen. So, all right. Hope you guys had a good day. Talk to you later. Bye. Maybe not yet. I should wait until I'm hidden. Stop recording. Okay. Bye. And stop recording.